Today we are dealing with the last subsection or subtopic of our module on tensors. So this is that will close it. So we are going to look into different type of coordinate systems and see how we can still apply the logic and the concept of operating with tensors in this. Right. So far we were dealing with the so-called Cartesian coordinates in the name of René Descartes. Descartes coordinates, also known as like that. And well, the Cartesius is just a Latin version of his name. Now, we in many cases you would want to actually work in different coordinate systems. For example, the cylindrical or a spherical coordinate system, depending on the particular geometry that you are solving your problem. That's where that would be more effective. Now, this is of course not a completely new concept for you. So you've seen these different curvilinear coordinates. The only thing that we're introducing here is what will be our way to write quantities such as tensors and higher order tensors in this new coordinate system, right? So because we were in Cartesian coordinate system, we had to we use the basis that was defined through the coordinate system. Now, how do we deal with if we change that to some other curvilinear coordinate system? Now, let's say let's start from one of the most important symmetries as a cylindrical coordinate system, right? With the some polar coordinate system, right? So, as an example, a more typical example that you would find would be when you consider a pipe that can be under pressure, or there can be fluid that is flowing through that pipe, and then it's through, because the geometry is reminiscent of the cylinder, so it makes sense to define everything in a different coordinate system that would correspond to this symmetry. So we can measure an angle, and we can measure the position of a radius of each point, and that basically defines the location of a point. So, and again, here is an example of in close to our topic of soft materials, is the arterial walls that indeed will be more convenient to deal with using the cylindrical coordinate system. Now, for the coordinate system, so we introduce this set of new coordinates. So we use here superscript 1, 2, 3 just to kind of distinguish them from the regular Cartesian coordinate system. And so these are generic names: alpha 1, alpha 2, alpha 3, and so now we are giving them the proper names here in our coordinate system. So again, that alpha 1 will designate as a radius, right, of any point, and so it will be radius of this point, and so phi will be an angle that we measure here, and together they identify the location of this point in the plane x1, x2, or in the space r and phi, and then the height of the point is measured by the coordinate z. And so this one is, of course, is not changed. It coincides exactly with the E3 or X3 coordinates, so they are the same. Now, now we can write these coordinates. We can connect them through the original coordinates in a pretty straightforward manner. So, for example, the x1 can be expressed in terms of right. So if we consider this triangle here, then the coordinate x1 will be nothing but r multiplied by cosine phi, and a very similar manner, I'm projecting here, it's probably not the best one. So if we measure x2 here, so then we need to consider different so we'll need to consider a different angle here, so so that is right here, and that will be exactly half pi, right, minus phi, and therefore we can say that this side of that new triangle here, right, is, apologies, that is not straight lines, but as it was meant to be, and so this side is will be r multiplied by the cosine of this angle, but this is sine of this angle, so that will be sine phi, because of cosine of half pi minus phi will be sine phi, so we get x2 here. And now this location here projected exactly here, so that will be exactly the same location as z. And we can easily reconstruct back the relationship, the inverse relationship of we can explicitly write what is r and what is phi, and so you can see, for example, that r can be expressed purely on the basis of the geometry here, so because that will be x1 and that will be x2, right, because these sides are equal. So they may not look like that because of my poor drawing here, but this is again x1, is x2, and then according to the relationship here in the simple trigonometry, you would conclude that r square is x1 square plus x2 square, and then for the relationship of phi, so the easiest way to calculate that is just to connect these two, x1 and x2, for example, and divide it, this x2, for example, by x1, and then you eliminate r immediately, and you will have x2 divided by x1 equal to sinus phi divided by cosine phi, and so you get to the tangent, and then you can express phi as arctangent of x2 divided by x1. So we also can conclude it based on the simple geometrical consideration of this triangle, and as we already said, so that's the simplest thing is here, of course. So if x3 equal to z, so z will be just x3. So in this way we establish here the relationship as a direct relationship connecting our original Cartesian coordinate components with their cylindrical counterparts, and also these inverse ones that we can express, and our cylindrical coordinate components in terms of our original Cartesian one. So that sometimes becomes important if you want to calculate certain quantities that are given to you in a cylindrical coordinate system or are defined in Cartesian coordinate system. This again not entirely new is for you, and of course you've seen that in different contexts in your previous courses, and so now we're going with that to actually to introduce a new concept. So by looking into that, so one important question is what is exactly our basis vectors here in this configuration? So before that we had this E1, E2, E3 that follow the coordinate system, the Descartes Cartesian coordinate system, and well, they were still mutually orthogonal, right? There were always 90 degrees between them. So now in this new coordinate system, what is this the basis vectors? How do we define it? So this is what we will do next. And so to this end, we define the so-called natural or covariant basis, and we will also have an opposite of that, which we'll call dual or contra-variant. We'll have properly introduced on the slide very soon. Now, this is how we define the natural basis vectors. Okay, and so you can see. So we put here the index that we put here will be here. So we'll not use it superscript for them. So that will be used for us to distinguish this natural or covariant basis with the dual or contravariant basis vector that we'll introduce next. Now, so this is general how we define it. So we didn't say what alpha is. So now we're going to specify that for our cylindrical coordinate system, right, where we know what is actually alpha is, right? So the alpha 1 is r, alpha 2 is phi, alpha 3 is z. And what we just have done on the previous slide, we also established the relationship between x and r, phi, and z, right? So that so the dependence is known. So if dependence is known, then we can go ahead and take these partial derivatives here according to 168, and then we can calculate the new components of this basis vector. Now, so let's start from SR. So right, so then basically so the first one SR, right? This will not be a number, so because we are now using a different coordinate system, so with different labeling. So the first one will be that SR, right? So and basically what we are doing here, according to 168, we just take each of these coordinates because this is again a vector. So each component of this we take the derivative with respect to r, right? So dx1 with respect to r, dx2 with respect to r, and dx3 with respect to r. Okay, so obviously x3 doesn't depend on r, so it's independent of r, it only depends on z. And x2 does depend on r in a very simple linear manner. So when we take the derivative of x2 with respect to r, the only thing that survives will be sinus phi. And here in when we take the derivative of x1 with respect to r, so the only thing that survives is cosine phi. So we expect here the result is to be cosine phi e1 plus sine phi e2. Okay, so that's the third component doesn't survive, right? So this is our SR. Now then, the next thing that we are going to do is we're going to the second one. So we're taking the derivative with respect to phi. So S phi. So put phi here and take the derivative with respect to phi. And so again, these structures again similar. So instead of r, the derivative with respect to phi, so so there is a little change in the notation, but the meaning is the same angle, just accidentally was changed. So the same phi. Now so again, x3 doesn't depend on phi, so just the only depends is on z, so we don't have the component a3 here, that will be 0. But e1 in the two components do depend on phi, so we take the derivative of cosine phi with respect to phi, so that the result will be minus sinus phi, and r is preserved, so that will be take the derivative with respect to phi, the result will be minus r sinus phi. And for x2, so it will be r cosine phi, so multiplied by e2, and so that will be our result here. So this is S r and S phi, And of course, for the last one, so that for z, so when we as z, so there is no dependence on z in this component of x1, so that will be 0 for x2 as well. And here the derivative of z with respect to z is just 1, it's unit, and so the result will be just e3. Okay, so we defined these natural or covariant bases in general, and we here in 168, and then we specified that for the for the cylindrical coordinate system. So this result in these three basis vectors for 169. So we can use these new basis vectors for to define our tensors. The only thing to notice here that while some of them are unit vectors, right? For example, cosine phi, sine z SR, so that will produce a unit vector. Obviously, when we try to project it to calculate the length of that vector, so we'll have unit. Obviously, sz is also a unit vector. But as it comes to, for example, s phi, so the length of that vector will depend on the coordinate r, so that in general may not be unit vector, right? And so if you want to work with unit vectors, then later on we will need to normalize it. But other than that, these are the vectors that are will be kind of pointing into the direction of these basis vectors that we need to define our basis vectors for defining tensors in the cylindrical coordinate system. So another important question for us to answer, and we will deal with that later, whether they are orthogonal to each other, where they are mutually orthonormal. So that, but we will look into that a little bit later. Now let's deal with the next guy. So there is another way, so how we can define this these basis vectors. So again, so there is the first way is to go with natural or covariant basis, defined as 168, but we also can do what is called dual or contra-variant basis, and they are defined now by 170 here. So the difference, if you know that, well, they still have a very similar composition of things, is that now we're taking derivative of that alpha, this components, coordinate components in the new coordinate system with respect to dx. So before that, we had the opposite. We had the derivative of x with respect to the alpha, right? Now we're doing this in different ways. And to distinguish the difference, so for dual and contravariant basis, we put this index here and the superscript I here. So before that, again, just to show you that, okay, so we use it the usual index notation to denote that. Now, okay, so now we what we will need again. So just to remind that what is our alpha, right? So that's still the same for cylindrical coordinate system, right? So we have r, phi, and z for alpha 1, 2, and 3. And now we will need to take the derivative of alpha with respect to with respect to x, right? So we will not need the direct relationship in terms of x expressed in terms of r and phi and z, but we need actually the inverse one. So, but we of course we already derived that, right? So now because we are going to take the derivative of r or phi or z with respect to x, right, with the corresponding vector here. Now now the structure is somewhat different, right? So you can see, well, there are some similarities, of course, but now we're taking the derivative with respect to the vector, and we did the similar operations before when we considered differential operators, and so now we're taking the derivative with respect to x. So then so for example for SR, right, so R will be, we just substitute R everywhere, but then we take the derivative with respect to the components of that x1, x2 and x3, right? and so all right, so let's take this this derivative of R with respect to, let's start from x1. So we are looking into we're basically looking into this expression, so we need to take the derivative of this expression with respect to x1. So this let's write it somewhere here. So that is the result will be such that, so we first take the derivative of the function with the root square, so we have half, right, multiplied by this x1 square plus x2 square and x2 square, and the power now changed to minus half, right? So we took the derivative there. Now we've seen that we need also to take the derivative of x1 square with respect to x1 to multiply it with that, and that will be 2x1, right? Now if we continue, right, so then so 2.5 here are gone, and we have x1 multiplied with this, right? And so, but now we can go back with definition of x1, so which is right here. So x1 is equal to r cosine phi. So we can take that and substitute it back in here. Okay, while for example this the so this and this 2 already gone, so that's okay. So and x1 is r cosine phi. Now x1 square plus x2 square root square is nothing but r, but there is a minus, so this whole thing will be 1 divided by r, right? So it's 1 divided by r, because again well so x square, so because r is equal to x1 square plus x2 square root square, and so if it's minus, so it will be 1 divided by r, so this whole thing here, and then x1 we just said it's nothing but r multiplied by cosine phi. So, and obviously at the end the result is that because there's r and r here, they're gone, so the result is very simple, cosine phi. So, and that is, so just to remind what we did here, so that was the derivative of dr with respect to dx1, right? And in very similar manner, we can you can see that that will be exactly a very similar it will be very similar too if we do this with respect to x2, and the only thing difference will be that here that will be x2, and then as a result we'll have a sinus phi here. And so so here we obtain cosine phi e1, and here we obtain sine phi e2, and obviously r is not dependent on x3, so that will be 0 here, and so again the result is for SR for this contra-variant basis SR, or dual basis as R, is cosine phi e1 plus sine phi e2. Now you can recall that that will be, if we go back, that will be actually the same as here, right? So let's see if S phi is any different. Now, so that's basically what do we do here. Again, to remind is just okay. So we still take the same derivative with respect to the components of the vector x, x1, x2, and x3, Now we need to look into phi here and derive it. Now this is a little bit tricky because I need to remember, well, this was straightforward. Now I need to remember what is the derivative of arctangents of some argument. And just to remind, so the derivative of the arctangent, tangent of an argument will be, okay, let's write it properly so we can follow that. And so if we take the derivative of arctan of let's use y, for example, so that the result will be, so we take the derivative, so that will be dot, so the result here is 1 divided by 1 plus y square, right? So that is if that's the result. Okay, I'm going to delete really quick the what we had before here to free some space. And so in our case, so when we take the, of course, probably would be more convenient to take it with x2, but it's back to x2, but okay. So let's do this with x1 as we need to do. And so the so we'll have a multiplication of so the derivative will be 1 divided by 1 plus we have here x2 divided by x1, right? x1, don't forget the square here. And now we need to take the derivative of the argument x2 divided by x1. So x2 of course survive, but we also have x1 minus 1, so that will be x1 with minus, right? So in that will be minus 2, right? Okay. Okay, if everything is correct, then we can rewrite what is here simply in the following way. So there will be x1 square that will eventually will go up. So there will be x1 square dividing there is x1 square here plus x2 square. Everything is correct here, and then we have still x2 here, right? And we also have minus x1 into the power minus 2 that will basically will just eliminate here with this x1 to the power 2. Okay. Right, so now let's change the color, red, just to say that okay, now we eliminated this guy and this guy because they have the same power, x1 2, so we have minus 2 to carry with us. And and so then we continue the derivative, then we ending up with x2 divided by x1 square plus x2 square, and then we can notice that x1 square plus x2 square is nothing but r square. So this is r square, okay? Alright, so this r square minus that we need to still carry with us. And so then x2 can be written as r sinus phi, right? R sinus phi. So that's we already derived before. And at the end of this short exercise, we obtain that we can also get rid of r and r square here, and the result will be minus sinus phi divided by r, and to remind us that was equal to the derivative of d phi with respect to dx1. Oh, right, that was unnecessary to have this long line here. Okay, so this is our final result for this term. Okay, so now we, in a similar manner, of course, you can also continue and take the derivative of phi with respect to x2. So again, the same relationship. You take the derivative of our tangent function and substitute, and so that will be a little bit easier, but the same logic will apply, and so you will then the result will be, so the first term is minus sinus phi divided by r, and the other term here is plus cosine phi divided by r. And again, of course, there is still no dependence of in the third component on x3, right? So when we look in phi, so there is depends on x2 and x1, but not on x3, so that is 0. And as we already discovered before that, for the last one, when it takes derivative of z with respect to x, so the only term that survives is the one that comes with the component e3, and so we have only e3 component here. So now we can notice, and just refreshing, going to the previous slide 35, that here we also had that e3 the same, and sr is also the same. The only difference is here, because you notice the structure is similar, but here we have a multiplicator of r, and here in the dual or contra-variant base that we define somewhat different, we are not multiplying with r, but we are dividing with by r. Then if thinking a little bit about that, we can notice that, well, this is just r will be a factor that will change the length of that vector, right, as phi, but it will not change the direction. So they still, these vectors will be in same direction. It's just we need to do, you know, when we do the normalization, we need to make them a unit vector. So then we need to divide them by different values, but they still are pointing into the same direction. So next, let's look into the relationship of our natural and dual bases, or contra-variant bases. And the important properties is that they are mutually orthogonal, meaning that if we take now this Si natural one, Si the dual basis, right? So again, to distinguish them, we have the upper superscript here, the index here, I here. And so if we take the dot product of these two, then we will have so the result will be so we'll produce the so then when they will be the same, so the projections will be unit. When they will be different, will be 0, very similar to the dot product of EI, EJ, when we had the definition of Kronecker delta and their projections here. Okay, and so actually you can see it right away, because if you put a dot product between them here, you will see that basically that can be written as the can be read as the chain rule when you take the derivative. So x can disappear, that will be just d alpha I divided by d alpha. Okay, so it's probably not a good thing to take the same indexes here, so we can distinguish them as we will do here. But then if you so that basically will change j here, and so the result will be d alpha j with respect to the d alpha I, but because alpha is basically, well, it's the same, it's just the difference will be in the indexes. So when the indexes will be the same, I will be equal to j, so then that will be 1. Or you can write it more explicitly write this index, write this in terms of the components and their bases in the coordinate system, and you will see similar structure again. There will be em and n dot product, and these are components, so we don't need that, and there will be delta mn, and in the end you have this similar to this chain rule, so that at the end the result will be d alpha j with respect to d alpha a. And just to remind again, so for our for this cylindrical coordinate system, you have so these are how they define these alphas. That doesn't matter again. So you can it still in general holds true, not necessarily only for cylindrical coordinate system, but also for any curvilinear coordinate system. And so obviously when I and j will be the same, so for example 1 1, so you take the derivative of r with respect to r, and that will be result will be 1, but in any other case it will be 0 when we're not taking the derivative of r with respect to phi and z, they're independent, so that will be 0. The same for phi, so when I equal in j equal 2, so it still will be 1. It's very similar to the delta function. Now basically now based on these two basis vectors, we have natural and we have dual basis vectors. We have two ways how we can write a vector, so higher order tensors in our curvilinear coordinates. Right, so that's okay, so again, so for vectors we have two ways how we can write, depending on what basis we define for us. Basis that will be contra-variant or covariant components. So so we can write it in these ways, right? So and so the components are then as usual we take the projection. If we want to calculate the contra-variant component, so we take the projection with si with the superscript, or if we want to take a covariant component, then we take the projection with this I with the subscript here to obtain the covariant component, and that's our standard operation, right? So before that we did that in the in our Cartesian coordinate system, but then we had only one basis, so we didn't need to distinguish these two. But that's exactly how we calculated the components. So we did dot product with the basis vector ei, and that gave us the three components that we want. Now, so with vectors we have two choices, right? What we can use for the basis here, right? So for the second order tensor, so we have a little bit more options, and more precisely we can do this in there are four ways how we can four representations, if you like, how we can write it for second order tensors. And you can see that there will be different combinations of things that you could write, right? So this so you have this so we can use only covariant, or we can use the contravariant, or we can use a mix of them. And then of course you remember that the order in the tensor product is matters, so we can change that and have as a covariant or contravariant multiplication here. And so you see, so to for this formalism also requires us to write these indexes as a superscript or subscript, depending on the formulations that we are using, right? So again there is still a summation notation that of Einstein that we still agreed on and using here, so that indeed works here in a very similar way as we did that for the for our in our Cartesian coordinate system, and now here you need to you have different levels of superscripts and subscript here. It is important to note here how we obtain these components. So the projections, and so this one, the contra-variant component Aij is obtained by multiplication of these contra-variants bases, and so the covariant component actually obtained by multiplication with those guys with covariant bases, and then as we go to these mixed ones, this contra-variant component, so we need to also maintain the order of this multiplication, so that basically that's for this one the contra-variant, and here this one, so it will be the opposite, so there will be Si superscript and Sj subscript. So these are just the formulas behind this. We will not be using this very heavily, so don't it might be a little bit confusing, but I just wanted to provide you with general guidelines of what's going on here. And when you encounter the bizarre indexes that goes up and down, and in the context of curvilinear coordinate system, you will at least know where it come from, and conceptually can what they represent and why do we introduce them. There are different ways how we can define a basis in curvilinear coordinate systems. Now finally, we are returning to the notion that these contra or covariant bases are not normalized, so they are not represented as unit vectors in general. And so, for example, so the first one, the component of the basis that correspond to the coordinate r, SR, is a unit vector. Yes, so that is right. And so if we try to normalize it, so the result will be returning exactly the same result. So we defined the normalized value gr. Of course, in this case, this is a redundant operation because we can calculate the unit vector, and the vector and the length will be unit anyway. But formally, we define it as the vector normalized by its length, so ensuring that this is a unit vector and the length of this vector is unit. Okay, because if we try to calculate this length, so it will be cosine square phi plus sine square phi, so which is 1 by definition. And so the normalized gr, so we introduce here the new 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 notation for the normalized basis. It will be exactly this. So it will be exactly the same because, well, the SR were both unit vectors. So now you remember that the second component S phi wasn't actually a unit vector. You can see that immediately here. So because it's multiplied by r, both components, we can pull it outside. So an r can be as large or as small as we need it, right? Depending on the position vector r. So it can be basically anything, and therefore the length of that vector will be actually r. So, and this is for the for S phi with subscript, for superscript. Remember that we have the inverse r factor here. So the length of this, also the direction of both of them will be the same, obviously, but the length will be different. So now the normalization here will be again such that, so now we're bringing it to unified unit vector in the same direction, g phi. And so if we take this one, so the length of this vector will be r, right? So the r square plus sine square plus r square cosine square. So we pull r square outside, and so cosine square plus sine square will be 1. So this r square and root square of that will be r. So here we just divide by r, and then very conveniently these two r will be dropping. And in this case, the same analysis will give us that the length of this vector is 1 over r, and so then now we divide it by 1 over r, and so of course they will drop, and then as a result, so we have this vector g phi will be minus sinus phi plus cosine phi, and obviously so this one is a unit vector. You can calculate the length. It will be sine square plus cosine square unit vector, as we had this before. And now, and finally for the third component, z, but that was very trivial for us, so it will be exactly the same here, and this is trivially a unit vector, so we can divide it, of course, by its length, by the unit vector, but it will not change the result, so this will be E3. And so, and once we define this, the length here, so one more thing that we can notice, that actually we can notice here that in the cylindrical coordinate system, so these basis vectors are mutually orthogonal, so they orthonormal, right? So if we trying to multiply them here, so then we will obtain that they are orthogonal, right? So this is so obviously that E3 is orthogonal to the plane component E1, E2, and so these two GR and G phi will be also orthogonal. All right, and so now when we have this normalized orthogonal basis, so then we have a unifying description of a vector, so don't need to choose between either this with superscript or subscript, subscript or superscript, this orthonormal basis. So we have just unified normalized one, and now they are identically exactly the same, because, well, they have to be the same after the normalization, so it's just unit vector in exactly the same direction as they were before. And so then any vector can be represented in terms of these components, right? So this is some arbitrary vector A, and so it has now three components, three basis vectors of different direction, and they of course orthogonal to each other, as you can see from here. Now this for vector, again, very similar to how we wrote it before in the Cartesian coordinate system, when we had A1, A2, A3, and that was accompanied by E1, E2, and E3. And now, but of course, so GR, GPhi, and GZ coincides with E3, but GR and GPhi don't coincide with E1 or E2, only for a very particular cases. When phi takes the values of 0 or the trivial one as half pi, but in general not, and so they will be different, and this is the function of phi, so they will be governed by the angle that define the location, right? Now for the second order tensor, we just, without really talking about that too much, so in a very similar manner I have 9 components of a second order tensor that now written in this bizarre way, instead of our usual dyadic products of a unit basis vector E1, E2 in the Cartesian coordinate system. Now in our curvilinear, this cylindrical, for example, coordinate system, we have this combination gr, gv, gz, etc. So still 9 of them, and the corresponding components that we actually can obtain without any problem, as we did by calculating the projection of the tensor on these basis coordinates that we did before with a double dot or contraction product. That's how we calculated the projection tensor. All right, so that concludes our introduction into the curvilinear coordinate system. So then the last topic that we'll touch here will be of how we do the differentiation. That will be in our next lecture. See you soon.